Right, good. So, good morning. We're going to go on a journey, Adventures in Spacetime. My name's Kevlin Henney. You can find me struggling with the technology. There we go. That's what we want. Okay. You can find me in a number of places online. Okay. I have an internet unique name, and we will be talking about networks, but not at the low level. Well, actually, no, at the very low level. I'm not going to be here to talk about network protocols. I'm also not going to be talking about the high-level stuff. But let's get into it. Let's just start off with one of the things I am actually known for is failure screens. People often send me failure screens. And this is one from Martin Fowler from a couple of years back. Kevlin Henney, you ought to know that United may have discovered a kink in the time-space continuum over the Atlantic, but sadly they weren't able to take advantage of it and get me home earlier. For those of you that can't see, what we've got here is time to destination 0. And the distance is distinctly non-zero. So the actual distance from Heathrow to Liberty Airport, Newark, the Great Circle route, is just over 5,500 kilometers. But I want to switch units. That's not centimeters, there's a space. This is really important. That's light milliseconds. Okay? It is just under 20 light milliseconds. Now, as a human being, a millisecond is absolutely meaningless to you. As somebody with ADHD, hours are meaningless to me. But what this means is that we confront, normally we think of software as just filled with abstractions. And people assume that things happen almost instantaneously. This puts a limit on certain things. If I have a server here and a server here, and somebody says we need to keep the data in sync with respect to 10 milliseconds, this is not possible. And it just doesn't matter how much your product owner says, you can do it, I believe in you. It's still not possible, okay? The laws of physics are standing in your way. And trust me, if you do make it possible, you don't need a product owner because you have a Nobel Prize, okay? This is one of those fundamental limits. It doesn't matter how hard you try. So there's another important consideration. For those of you that were in the keynote, Mark was talking about various considerations of a system, constraints and fitness functions. Fitness functions need to not simply respect the ideas that we have about performance. They need to respect the reality. So there is a bounding limit. So that c, it is the speed of light. Speed of light has a very precise definition. 299,792,458 meters per second. This is exactly the speed of light. This is not approximately the speed of light because it's actually the definition of the meter. The meter is defined, and has been since 1983, as 1 over this. How far does light travel in a vacuum? In 1 second, well, this is the fraction. That is the meter. So tomorrow, if the speed of light changed, the meter would also change, yeah? But nobody would notice because the universe would be a catastrophe at that point, okay? The point here is that, let's just round this off, okay? Basically, what this means in practice is the distance across a piece of A4 paper or across the top of my laptop is around 1 light nanosecond. And we think of the speed of light as being fast, but it actually has some there's some constraints. 1 light nanosecond, that's not very far when you consider how large a processor is. It means that from one side to another of a processor, you are going to be limited to gigahertz. You are not going to rise above gigahertz, okay? This is really important. This is not a question of technology. This is a question of physics because of the distance. If you look at a modern chip, they're quite large. But to get from one side to the other, we are actually having to engage in caring about the speed of light. The distance to the moon is just over a light second. The distance to geostationary orbit, where many communications satellites are, is about 1/10 of a second. So therefore, up and down is 1/5 of a second. Why does that matter? Because you notice 1/5 of a second. One fifth of a second is above the threshold for usability responses. And if you ever use a satellite phone or any long distance call that goes via satellite, you will notice a very slight delay, and it's just enough for you to get the synchronization with your calling partner wrong. And that's only 1/5 of a second. It turns out we're very sensitive to this. So we might not be sensitive to milliseconds, but go above that, and we are. So let's talk about C. It's a constant, but that's not what it stands for. It's from the Latin celeritas, meaning speed or fast. But it's also, interestingly enough, C is in causality. The speed of light is not simply to do with light. It is the speed at which events can happen. It is the speed at which gravity waves travel. In other words, events cannot cause one another faster than this in the universe. Now, this has some interesting implications. So here's a paper from the late 70s by Leslie Lamport. And in this paper was a landmark paper, 1978, because what he observed, it's one of those papers that has this kind of nice title, it's very understated. Time, clocks, and the ordering of events in a distributed system. It's just like, okay, there's something going on here. Really important paper. He talks about how to sequence events in a distributed system. You cannot assume that the time told by a device over there is the same as the time that you're working on now, even if they are set to the correct time. But the other thing is you also need to remember, never trust another machine. Okay, never trust another machine. Do not trust the timestamps on another machine as your source of truth. Timestamps will only give you local ordering. So, in a distributed system, it is sometimes impossible to say that one of two events occurred first. And this is interesting because this is not a limit of technology. We're actually tapping into something fundamental in the universe here. The relation happened before is therefore only a partial ordering of the events in the system. This happened before relationship was introduced in this paper in the late 70s, and it turns out to be really important for reasoning about distributed systems and concurrent systems. It's very important when dealing with things like memory ordering, when dealing with threading. So we have found that problems often arise because people are not fully aware of this fact and its implications. Now, when I point these things out to you, most of them are surprising, interesting, or obvious. But that's not how you feel when you're coding. When you're coding, everything's hidden behind layers of frameworks and middleware and abstractions. You're looking at the world through your IDE. And it's very easy to forget that this stuff actually happens and that there are limitations. We'll explore a couple of these. So there's a notation. A before B, or A happened before B, means that it is possible for event A to causally affect event B. This definition will appear quite natural to the reader familiar with the invariant space-time formulation of special relativity. This is my favorite sentence in the whole paper, because it just casually drops. Who here is comfortable with the space-time formulation of relativity? Okay, right. So I do have a degree in physics, and I'm moderately comfortable with it, but it's just not the kind of thing you're expecting of most software developers. It's just casually dropped in there. What's interesting is that he then goes on to show a bunch of diagrams, and I remember looking at this paper going like, hey, wait a minute, these are space-time diagrams. I've seen these before. So, let's talk about this term, space-time. Sometimes it comes with a hyphen. It's much cooler without a hyphen. Space-time is a formulation. Concepts of time and three-dimensional space regarded as fused in a four-dimensional continuum. That's very cool. Okay, this is also known as Minkowski space. It's down to Minkowski's formulation of relativity, or interpretations of relativity. Useful in visualizing and understanding relativistic effects, such as how different observers perceive where and when events occur. Let's talk about the word adventure. An unusual, exciting, and daring experience. That's what you're doing right now. Excitement arising from such experiences. I can't really promise you that much excitement. Hopefully you'll get something from this. The encountering of risks, you're safe, it's okay. The most dangerous thing that can happen here is I fall off the stage. A hazardous or perilous enterprise or performance. Right, okay, now we're talking. Let's talk about enterprise. Let's talk about a couple of things here in terms of the fact that we live in an era where we have commodified and standardized the tools and frameworks and approaches that we use to build the applications that we work on. And they are normally in some sense distributed. So Martin Fowler wrote this book, Patterns of Enterprise Application Architecture. It's over 20 years old. It's still good, but I'd say that many of the patterns and techniques have moved on. Obviously, this book doesn't mention cloud, it doesn't mention microservices, it doesn't mention DevOps, because none of these words had been invented. Some of the balance of processing that you find between server and client has changed. The technology set has changed. But at the same time, there are some underlying principles here that still remain true. And there are some techniques that you can still keep in mind. One of the ones I think is really interesting is that he picks up on Lamport's observations and proposals, and he describes a Lamport clock. Use logical timestamps as a version for a value to allow ordering of values across servers. This is really interesting because most people think, oh, we'll just keep a timestamp and hope that the clocks are all correct. I'm just going to say this again. Never trust your local clock, okay? Or never trust that you have the right time. And people often say, yeah, but Kevlin, but we synchronize with this. No, which bit of never trust are you struggling with? This statement is not open to ambiguity. Your clocks do not always work. This is one of the most important things we're going to discover about distributed systems. You can trust nothing. But there are some things you can do in spite of that. Because if you want to relate it to real time, that's fine. You hold an adjacent timestamp based on your local time. But we can create a logical time for when we actually care about the ordering of events. In Mark's talk, he mentioned that distributed systems are really hard to debug. I've already given you most of the reasons, or some of the reasons why. Because we don't know what's happening when, and finding causal relationships between things is kind of key. So we can actually create a causal ordering. We know that send must happen before receive. Otherwise, congratulations, you've invented a time machine, and there is a Nobel Prize waiting for you, okay? The sender, what they're going to do is they're going to hold some kind of counter and let us not worry about what happens if the counter overflows, okay? That's a different talk. We're going to hold just some kind of counter. Okay, it's not actually a time-based thing, it is just a counter. So, we're going to increment it. Every time we're going to do something that might be significant or visible to somebody else. And we want to create an ordering. Okay, so what we've got here is we have a receiver. The receiver is going to receive a message. This happens afterwards. They are going to receive a message, and what you do when you send a message, you send your version of the time. The other person receives the message and the time it was requested. What they then do is they then adjust their local time. They say, it's the maximum of whatever I believe the time is, and whatever you told me the time was, plus 1. This means it's monotonically increasing. It doesn't relate to an actual time of day, but there is an idea that it's going to give us an ordering over of significant events across a system, and therefore we can say what happens before. So if you do care about this kind of stuff, hold a timestamp that's an actual time according to whatever device you're on, but also hold this, because this is the one that will tell you the sequence of events in a system. There are various things. We do obviously have things like network time protocols, and we can actually have incredibly precise times across the network, but these all rely on your network always working reliably. These are incredibly powerful and incredibly reliable. But given that we're talking about protocols, I'm not here to talk about the basic protocols, things like IP, TCP are layered upon it, or worry about HTTP, or moving up the stack, any kind of approach that you might be layering on top of this, or even about the technologies and paradigms that we might use. A remote procedure call intending, for example, the way that we hide all of this lower level stuff is by presenting people with an illusion. Remember, most software is illusion. We're creating an illusion. A remote procedure call, the whole idea is it's like a procedure call. That means in my code, I don't have to think about low level stuff. So I create an illusion. Software is very good at that. We have particular technologies around this. But we need to always remember behind the illusion there are other properties. We build in terms of services or microservices, although to be honest, most people, when most people use the word microservices and they describe them to you, most people are not doing microservice-based architecture. They're just doing good old-fashioned services, okay? Just with a different technology stack. They are not micro for anybody's definition of micro. They certainly have interdependencies, which microservices are not supposed to do. But microservices sounds cool. So people say that that's what they're doing. And if that helps you, that's great. So a number of years ago, I co-authored some books on patterns, including Pattern Language for Distributed Computing, Poser 4, where we explored, as it was nearly 20 years ago, the perceptions of the stuff that we have in a distributed system. And honestly, most of this does actually still stand up because we were talking about design principles and patterns rather than specific technologies. And we gave a definition of a distributed system. A distributed system is a computing system in which a number of components cooperate by communicating over a network. Yeah, it's not a bad definition. I go with that one. I think that's pretty cool. We'd be very specific here. I actually like Leslie Lamport's definition, possibly a little more. A distributed system consists of a collection of distinct processes. I like that he's made that point. Distinct processes which are spatially separated. Again, it already sounds cooler. And which communicate with one another by exchanging messages. He doesn't talk about networks or anything like that. I quite like this as a more general definition. But there's an even more general definition that Leslie Lamport is perhaps more famous for. And if you haven't come across it, today is the day. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Yeah, everybody relate to that one? That's a distributed system. It's like, damn it, I can't do any work. Oh, why? Because something somewhere is not working. This is fine. This also introduces us to an interesting concept, one that we're going to come back to, which is partial failure. Partial failure. We have the idea of not failure, success. It's always working. We have the idea of complete failure. Nothing's working. Partial failure is this thing's working, but that thing's not, simultaneously. If you work on a single process architecture, everything's inside a single process. If that process crashes, that's total failure. If, on the other hand, you have a process talking to another process, and the other process is still going, then you have partial failure. And the problem is that total failure is very easy to reason about. It's very ones and zeros. It's working, it's not, we're done. Partial failure is hard. So, there's a bunch of things here. Let's find out a little bit about your familiarity with some of these ideas. Who's heard of CAP theorem? Okay, excellent, great. Who's heard of the fallacies of distributed computing? Okay, that's slightly fewer, okay. Who's heard of a note on distributed computing? Okay, we're down to 0. Who's heard of answer? Yeah, just to let you know, I've run this talk a couple of times, that's the normal thing. Quite a few people have heard of CAP theorem, fewer have heard of fallacies of distributed computing, maybe 1 or 2 have normally heard of a note on distributed computing, nobody's heard of answer. So answer is advanced network systems architecture. It was a study and a project undertaken in the 1980s and early 90s in the UK. It was research. It was not very widely publicized, which is why nobody's heard of it. But for me, it was very influential because I did a master's degree in parallel computer systems. And this was happening at around the same time. And this is how we were taught distributed computing. And what I find fascinating is this was very much ahead of the curve. And things like the fallacies of distributed computing, note on distributed computing, and CAP theorem all came afterwards, but simply repeat what we already knew at the end of the 1980s. So you can actually find a whole bunch of stuff on this online, Computer Conservation Society. I looked 5 years ago for stuff on answer. There was nothing, and now there is something. So it's not, as I say, it's not very widely known. There's a whole lot of guides. This is a system designer's introduction. There's also an software engineering, an architect's introduction from a couple of years before. There's a whole load of stuff here. But one of the things that I found really powerful when I was taught this and how to think about distributed systems, first of all, is an idea. We heard Leslie Lamport talking about this set of assumptions. He says, this document says, it is important, therefore, to identify explicitly the assumptions which are made for non-distributed systems. and to ensure that they are absent from the models for distributed systems. In other words, what are the assumptions we normally have about how we code? What are the assumptions we normally have? And the problem about assumptions is they're normally invisible. You don't know you have them. Yeah, assumptions are invisible knowledge. And then you don't know you have them until you hit your toe on them. And they described a distributed system in terms of negative assertions or negative assumptions. In other words, you want to avoid these. Single global namespace. Not everything lives in the same space. Global shared memory. That's a kind of extension. In other words, the first one is about addressable. Can I refer to things in the same space? Global shared memory. These are related. The idea is we don't have global shared memory. When you are working with a normal object model and a conventional programming language, all of your objects are in memory. You can just pass one reference to another and life is easy. You don't have that. Global consistency. Now it gets really interesting because these are very obvious limitations in one sense. They're spatial, but consistency is very subtle because this is time-based. Consistency means that we both have the same view of a particular piece of data. If I think I've updated a value, and you've yet to receive that message, I don't know that you haven't received that message necessarily. I don't know that you don't know that I've changed the value, particularly when we introduce things like failure. Sequential execution. Now, this is a very interesting one because pretty much all of our coding is based on thinking about sequence, okay? So, let me think. How should we ask this one? Who here is working in an environment where their code is actively creating threads? Okay, that is very few people. By the way, that's typical. That's good, because threading is a nightmare. You know, it's just one of those things that, in spite of the fact that I have a background in parallel computing, I generally go around telling people, please don't put threads in your code. Because the chances are you're going to make things worse. Because it's difficult to reason about, or particularly it's difficult to reason about with respect to state change. The problem is that in a distributed system, everything is concurrent for free. You don't get a choice. That's it. It just is, because that piece of hardware is running independently from your piece of hardware. But why is this such an issue as an assumption? Because all of our programming languages, by default, present us with a sequential view. And even if you are working in a programming language that supports threading, it doesn't look like it supports it. In other words, the syntax, I want you to think about the syntax of the code on your screen. You read from top to bottom, that's sequence. You indent according to logical flow, ifs and whiles and things like that. Do you have parallel structures in your programming language? I'm just going to save you the trouble of the answer. No, you don't. Okay? I mean, there's a chance that one or two of you might be using a language that does, but you don't. Okay? None of the languages that are in the mainstream have a good visual representation of concurrency, of parallelism. In other words, that's one of the reasons it's hard, is we don't have a notation that makes it first class. It's normally through libraries and other things. This is a problem because we know that the network is concurrent, but we sometimes don't feel that, we don't remember it, and then we're surprised when stuff, happens. Total failure. We're surprised when things don't happen. Synchronous interaction, okay, that this is an extension, if you like, of sequential execution. I call something, I wait for the response, I get it back. That's really easy to reason about. What you normally get is something asynchronous. Locality of interaction. Everything is local and therefore reliable. Fixed location. Things migrate. I mean, this is even before we had mobile phones, this observation was made. You cannot guarantee that you're going to have the same IP address in the same place all the time. And direct binding. That you can actually directly connect to something and it will always be there. And similarly, homogeneous environment, that everything on your network is running the same technology. So we can pick out various things. Sequential execution. One of my favorite observations about this. 10 things you'll find shocking about asynchronous operations. Yeah. Total failure. This was a good one. My publisher, a couple of the books that I've published, O'Reilly, fire in California, can't read your ebook in Pennsylvania. Yeah, perfect example of Lamport's observation and definition of a distributed system. But it also gives us an opportunity to talk about some of the myths. When we talk about resilience of a network, sometimes there is this myth. And there is even a website that kind of talks about these various myths. The internet was invented by the Pentagon and designed to survive a nuclear attack. This is a really widely held myth. There was even a small point where I was repeating this, and then fortunately, I kind of watched a couple of things that kind of clarify that. Truth, whatever role, so the idea that this was true was popularized in the early 90s. The truth, whatever role you wish to attribute to ARPANET as regards the origins of the internet, it is clear the early internet was not motivated by considerations of nuclear war, but by a need for technical protocols to allow computers and their users to communicate. ARPANET was primarily an early computing science exercise rather than a military one. So it was not designed with nuclear wars in mind and their resilience. That's kind of a nice product. This is a classic example of some of the myths that we hold. So let's move from myths to fallacies. The fallacies of distributed computing originated at Sun Microsystems. It was compiled by L. Peter Deutsch, and from the mid-90s onwards, it was popularized from the late 90s onwards. Bill Joy and Dave Lyon. Bill Joy, if you're not sure about, Bill Joy was one of the people responsible for BSD Unix and creator of the VI editor, which ultimately led to Vim. Dave Lyon had already formulated a list of flawed assumptions, again, this idea of things that you incorrectly believe but might not be aware that you're believing. Okay? In other words, habits that when they're pointed out to you, oh yeah, of course I know that about distributed systems, but you don't know that you're doing it. So when you're coding, you're just thinking in terms of the code in front of you and the APIs you're calling. You're not necessarily thinking about physics and weirdisms of distributed computing, because what's presented in front of you is a very simple and simplified and rational worldview. That's a good illusion. That's what software is about. Assumptions about distributed computing that were guaranteed to cause problems down the road. The network is reliable. Yeah, okay. So here's a good example, a major unreliability. This happened in 2018 in the UK, early December. The O2 provider, more than 30 million mobile customers unable to get online. So this happened for about a number of hours in the day. Population of the UK is about 65 million, so you are dealing with a lot of people who cannot get online. Other things to notice is this was early December, so we're heading into the Christmas market. Business is ramping up, and so are people's expectations. This is a bad time to have a network failure. You cannot guarantee stuff works, okay? Latency is 0. Now this one, I see this everywhere. If I told you that the speed of light means that you have because of the speed of light, things do not happen instantaneously, you go, well, yes, of course. But if you're working on a web app or a mobile app, I bet there's a very good chance that you've done something like this. Right, let's go and look at that again. It's what I call the oh shit moment. The oh shit moment is where you go online and you look at something. For example, maybe it's your bank account, maybe it's stuff in your basket, maybe it's the things that you have previously purchased, and there is a moment where it says you have nothing. And that list is empty, and it says you have 0 items, you have 0 things. And you go, oh shit, I'm sure I spent money on all of this. And then a moment later, it updates. Whoever wrote that believes in 0 latency. They believe that everything is instantly available. I have this just this morning. The recent disastrous updates to the British Airways website have actually made a bad site worse. I am considering flying various Romanian carriers next time. It's disastrous, but one of the things is when I go to the website, the button appears saying log in, but I'm already logged in. And then a moment later, it says, oh, hello, Kevlin. Well, why did you tell me to log in and then half a second later change your mind and realize I'm logged in? Because the developer believed that information is instantaneously available. So, What's going on here? John Carmack identifies this problem. A large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may be in. This is really important because what most people are doing is they're saying, oh look, I have a collection. It's a collection of things. It is a state of whether or not you're logged in or not. It's a collection of your stuff. And what is that collection when you create it? Well, I think you all know that when you create a new collection, unless you're using a very weird library, your collection is initially empty. Now, this is where you need to understand. That's not reality. It's an empty collection. It doesn't actually reflect anything to do with your orders. And so what they do is developer assumes, oh, it's displayable. And so they display a thing that has an empty collection. And then there is an event that says, oh, now it's been loaded, it updates, and then they redisplay it. This is not the correct way to program it. The technical term for this approach is a bug. That is a bug. If you are showing people it's empty, oh, I've changed my mind, that is not right. The collection is 0, but that doesn't mean you have nothing. That means the collection is empty. What it means is we are loading. There is a big difference between we do not yet know the answer because we have not received the answer, and the answer is 0. We are loading. Now we have loaded, we display. In other words, what does this look like? There we go. That was easy. It's not the hardest piece of code in the world. But almost every site violates this because people assume that it's instantaneous. Yeah? There is a difference between we don't know and 0. Huge difference. This relates to another concept. Bandwidth is infinite. Speed is not infinite, bandwidth is infinite. The thing you have to remember is nothing in nature is truly infinite. Okay? Nothing. There is no such thing as infinity. I'm going to be absolutely clear about this. Infinity is made up by mathematicians. It's big math trying to sell you big numbers. Okay? Infinity is a mathematical fiction. I'm not saying there isn't some profound stuff in mathematics, but mathematics is not a fundamental concept of the universe. The universe is the fundamental concept of the universe. When a physicist says, for example, with black holes, at this point, the density becomes infinite. When a physicist uses the word infinity about their theory, what they're saying is it's broken at this point and we have no idea what's happening. Okay? That's a polite, so in other words, I want you to just we could do this as a customer test. Physicist says this tends to infinity or this becomes infinite sounds much more cooler and poetic than, honestly, we have no idea what's going on here, our theory is broken. Okay? That's physicists saying it's broken. When a physicist uses the term infinity, it means they don't know, and they don't want to say that. Infinity is created by human beings. In fact, I live in Bristol in the UK. We have a local brewery. See, they make infinity. You can get it by the pint. Yeah. So infinity is bounded. But I will say, I'm trying to pick a fight here. Anybody who's a mathematician, if you think mathematics is fundamental, come and talk to me afterwards. We'll sort this one out. You're wrong. Okay. The network is secure. Oh, no it isn't. We know that one. So, that was the original 4. James Gosling had actually codified these 4, calling them the fallacies of network computing. These are the original 4. On top of that, LP de Deutsch wrote the list, this time 7 strong, into a slide presentation. What 3 extras did he add? Topology doesn't change. Your network will reconfigure. You cannot guarantee that you have a fixed arrangement. There is one administrator. Yeah, that's not going to happen. Transport cost is 0. This refers both to latency and also the cost of maintaining a network. Gosling added the 8th fallacy in 1997 or so, by which point we then have the 8 fallacies that we are familiar with when you go around and you Google fallacies of distributed computing. And the 8th fallacy is the network is homogeneous. This one sounds familiar, because it was identified 10 years before in Answerware. So this is why I find it quite funny, because the fallacy, I remember when somebody said, oh, are you familiar with the fallacies of distributed computing, Kevlin? And I said, what do you mean? And then they listed them off, and I said, Yeah, but doesn't everybody know these? No, they didn't. So it's good that somebody's there to kind of, most of history is about revisiting history and reinventing it. Many people have tried to add more to the original 8. Most of these are either inconsistent with the previous 8, or they're not saying anything special, or they're too specific to a particular technology. But as Deutsch was the originator of these, he's allowed to add one. Really, expansion number 4, it extends beyond the boundaries of the physical network. The party you are communicating with is trustworthy. And this is important because often we assume, and this is important, this is to do with trust. And trust is not necessarily that the other person is a good person or that they are a bad person. It turns out that you don't have to have somebody be a bad agent to have problems and have trust issues. Everybody remember CrowdStrike? Yeah? Yeah. Friday the 13th. Obviously, 13 is in hexadecimal. Friday the 13th last year. This is one of the biggest security incidents in history. And it wasn't actually a malicious actor. It was an act of error and mistake. As I collect error screens, somebody highlighted, Bryce from NVIDIA highlighted perhaps the greatest Kevlin Henney event of all time, CrowdStrike. And then we have, busy day for you, I suppose. Yes, it was. I got a lot of people atting me various fail screens. Back to that O2 failure. What caused it? What caused 30 million subscribers to not have this? It was an expired certificate. So trustworthiness is not sometimes people, when they think about trust, they think about like, oh, somebody's after stuff. No, trust is about reliability. It's, can I trust you to do the right thing? Can I trust you to make sure that you remember to renew your certificates? People have a blind spot when it comes to understanding their architecture. They normally think, our architecture is this, that, and the other. They have a tech stack. They have a set of ideas about what the code does. Certificates are not my problem. I'm a developer. Certificates are not my problem. I'm the architect. I'm a technical guy. Certificates are your problem. Because without them, your system doesn't work. It doesn't matter how good your code is. If it can't run, it doesn't matter. So, there is a thing called Hanlon's razor. There are various phrasings of it. I'll use a polite one. Never attribute to malice that which is adequately explained by incompetence. Somebody doesn't have to be malicious to not be trustworthy. They can just be incompetent. Okay, so a note on distributed computing. Jim Waldo, Jeff Wyan, Ann Walrath, and Sam Kendall. Clearly, the main criteria for this was that your name begins with W. These folks worked at Sun. What is really interesting is there appears to be no relationship between this and the other people at Sun who came up with the fallacies of distributed computing. I am kind of fascinated by that. There are fundamental differences between the interactions of distributed objects and the interactions of non-distributed objects. And this is really important because whatever paradigm you're using, if you're using a procedural paradigm, remote procedure calls are not exactly like procedures. If you are using an object paradigm, remote object access is not like local object access. Distributed object-oriented systems based on a model that ignores or denies these differences is doomed to failure. And then the paper goes on to list pretty much everything that we already knew, but puts it in a different form. Martin actually kind of took this idea a bit further. You can't just take a group of classes that you design in the world of a single process and come up with a distributed model. Hence, we get to my first law of distributed object design. There isn't a second law, by the way. Don't distribute your objects. There we go. That's a nice, easy one. Okay, so the final thing, the CAP principle. Now, the CAP principle has gone through various formulations. It was actually originally a conjecture. And then it was a theorem, eventually. So we know it's a CAP theorem because it's actually been proven. It was known actually also as Brewer's conjecture, named for Eric Brewer, who came up with it in the late 90s. This is the paper in 2002 that makes a proof of it. So it turns it from conjecture into theorem. Seth Gilbert and Nancy Lynch. And they say, when designing distributed web services, there are three properties that are commonly desired: consistency, availability, and partition tolerance. It is impossible to achieve all three. To be precise, when we say to achieve all three, sometimes people have misunderstood this as you can never have all three. That's not true. In a fully working network, you will have consistency, you will have availability, and you will have, well, if it's working, you don't need partition tolerance. The idea is that you cannot guarantee all three. There's a subtle difference between this wording. So, consistency. What do we mean by consistency? I kind of hinted at that earlier on. Consistency is where I have a piece of data and you have a piece of data that describes the same thing, and that they are consistent and the same. We could imagine this very simply as if the two of us standing side by side on different phone networks looking at some social media. And I'm looking at somebody's feed, and we both do a refresh, and we look at somebody's feed, and we both see the same things. Your most recent posting, your most recent update, there it is, I see the same thing. That's consistency, okay? But this isn't just about social media. This is obviously about values and money and things that we expect in a network. Availability, oh, by the way, the thing about consistency is we are absolutely guaranteed that if the network is working, we have the same value. If the network is not working, we do not receive the wrong answer. That means, let's just say that I'm not on O2, but let's just say that O2 has another outage, and I happen to be on O2, and you are on a different network, and we both look at the same thing. Mine will say network not available or could not refresh. That's what consistency means. It means I will not give you an answer that is not up to date. You either get an up-to-date answer or you don't get an answer, and I tell you you don't get an answer. I give you a failure indication. Availability is I always give you an answer, but I can't guarantee that it's right. Okay, in other words, I might be related, this might be working off a cache, okay, and we're looking at different values, and mine doesn't seem to update, okay? So, I'm always getting an answer, but I can't guarantee that it's consistent. Partition tolerance, this is a slightly weird term, partition tolerance, so let's define what it means. I kind of just wish it had been called tolerance, but here we go. What do we mean by partitioning? Here's a network. Good? Yes? Excellent. Right, what I'm going to do now is I'm going to knock this node out, and what happens next is a network partition. What happens is, let's just say we've killed a router. That now means we've got two networks, okay? It's partitioned. Now, partition, so we can basically describe it as a not work, or for those that read Russian, a yet work. But the basic idea is that whatever, and it doesn't just relate to knocking out routers, it causes any failure, any server being down, something not working. And what we can say is that I can offer you guarantee. I can guarantee that the system, from your point of view, will continue to work, and I will give you consistent values, but if the network is not working and I cannot make the value get an update to it, I will show you that there is an error indication. I will show you that there is a problem, but I cannot guarantee consistent availability, or rather continuous availability. Or I can guarantee you will always get an answer, but I cannot guarantee that it's consistent. But when there is a network failure, I can still be running. It won't crash the client, for example. Or I can guarantee both of these. In other words, you will always have a consistent and available result, but in the face of failure, it all falls apart. This is actually the guarantee that you get for single process applications. So the point is that we can't guarantee more than two of these. This is effectively an observation that is captured nicely by Douglas Adams in The Hitchhiker's Guide to the Galaxy. We demand rigidly defined areas of doubt and uncertainty. Okay? You cannot guarantee this full and complete knowledge. It's kind of, this is Heisenberg's uncertainty principle. If you like, CAP theorem is Heisenberg's uncertainty principle, but for the network. But this leads to things like eventual consistency. But we need to also be sure that we understand the design consequences. So yeah, we're getting there, don't worry. I'm eventually consistent. I eventually shut up. We started a couple of minutes late. Okay, you have two orders. Okay? 1, 2, 3. Has anybody ever seen this? You're looking at a screen, And it says, you have n things, and then you look, and there are n plus 1 things. And sometimes people go, oh, that's eventual consistency. No, it isn't. That's bullshit. That's a technical term. Because the point is, you've got a collection that you've actually displayed, and on the same interface, you tell me a lie. You've just shown me 3 things, and now you're saying there's 2. What's happened is these 2 have come via different data paths. The correct answer is you have 3. If you displayed 3, you had 3. This has nothing to do with eventual consistency. This is something that people, when you're in the same process, as I observed, it is a feature of a distributed system that it may not be in a consistent state, but it is a bug for a client to contradict itself. If you are in the client, you are in the same address space, you're in the same piece of code. If you've got 2 different values, you sort it out. Don't display 3 things and tell somebody you've only got 2. You ignore the one that's wrong. In fact, you don't even need the other one. You always go with the displayed truth. Okay? These inconsistencies do arise because of data paths, but it's your job to fix it. It's also exacerbated by things like micro front ends, but that's not a true cause. So, in closing, the concept of time is fundamental to our way of thinking. This is Leslie Lamport's observation. It is fundamental to our way of thinking, but we are often surprised when it doesn't work out that way. And we often don't notice these things. And we sometimes sort of say, oh, well, that's just a feature. Or, you know, that's not a big deal. The user can figure it out. No, that's what software is. Create a consistent illusion. You figure it out. There are things that you cannot do, but some of these things you can. But always be reminded of them. Douglas Adams observed that time is an illusion. Lunchtime doubly so. Thank you very much.